Hello, my name is Hugo and I'm a PhD student at the Institute of Computing at Unicamp, Brazil, under the supervision of Professor Lehilton, who's also a co-author of this work. Firstly, I'd like to thank the opportunity to present this paper, a true approximation for the K-prize collecting Steiner tree problem, at the 14th Latin American Theoretical Informatics Symposium. Thank you. Unfortunately, due to time constraints, the presentation will only cover a simplified outline of the results. We present a practical scenario for the problem before formally defining. Then we quickly define what a laminar structure is, and then an overview of the algorithm. Okay, suppose we have been employed by the government to deploy a network infrastructure to connect a set of cities, and suppose we have to pay a penalty for cities not covered by the network. Since cables are expensive, looking at the scenario, we then decide that connecting the cities with cheap penalties are not worth our budget. Hence, we decide to deploy a network covering only the two most expensive cities. But foreseeing our slide design, the government asks for at least k cities to be connecting this network, which in this case is 3. Thus, we end up connecting the city with penalty 10 to the network, and the one with penalty 25, because it was close enough to the network to be worth it. Okay, so formally, the k-prize collecting Steiner tree problem is defined as follows. We are given a graph G and a root R, edge lengths for each edge, a vertex penalty for each vertex, and a value k. And our objective is to find a tree T that spans at least k vertices, including the root, that minimize the cost of the edges in the tree, plus the penalties of vertices not spanned by the tree. In this example, we have a graph where edge lengths are written on the edges and penalties are written on the vertices. K equals 4, and this is an example of feasible solution which spans 6 vertices and costs 8 on the edges and 11 on the penalties, totalizing a cost of 19. If k equals to 0, the problem will reduce to the prize collecting Steiner tree, which is NP hard to approximate within 1.01. The current best approximation has a factor of 1.97. If every penalty is equal to 0, then the problem will reduce to the k minimum spanning tree. It is also NP hard to approximate within 1.01, and the current best approximation has a factor of 2. For the k-prize collecting Steiner tree, we have a 5 approximation by Han, a 3.97 approximation by Matsuda and Takahashi, and a 2 approximation, which is this paper. We say that a collection of subsets of vertices is binary laminar if for distinct subsets in the collection, either they're disjoint or one is a subset of the other. And if any subset L of size at least 2 in the collection, there are 2 other subsets such that their union results in L. We also denote by placing a star the inclusion-wise maximal subset in the collection. In this example, all the circles are subsets contained in the calligraphic L collection, and the circles in red are the ones in the collection calligraphic L star. Firstly, we briefly present a primal dual scheme that's very similar to the one by Goemans and Williamson. The algorithm grows a forest F maintaining a binary laminar collection calligraphic L, such that edges of F never cross subsets in the calligraphic L star. It also maintains a collection of tight subsets B, which is used to prune F at a later stage. In the algorithm, costlier penalties leads to less subsets to be included in B. It also maintains a vector Y with an entry YL for each L subset of V. And in our particular algorithm, Y is not actually a feasible solution for an LP relaxation. We actually compare Y directly to an integral solution. The algorithm is split in 2 phases. In the growth phase, it starts with calligraphic L as the collection of singletons and with a forest F without edges, and it increases the variables YL of each L in the calligraphic L star until an edge event occurs, where an edge is included in the forest F and a new subset is included in the calligraphic L. Or a subset event occurs, where we include a subset in B. This is done iteratively until F is a 3. Then, in the pruning phase, it deletes exhaustively from F subsets in B that has degree 1 on F, and we retain a cleaner tree F. Here we present a simplified flowchart of the algorithm. In this example, we give priority to edge events over subset events. As a direct consequence of a previous result, we know that if the resulting tree F spans at least k vertices, then this is a true approximation. But what if F spans less than k vertices? then we can increase the penalty cost of each vertex by lambda, since higher penalties lead to larger tree f in the algorithm. But if lambda is greater than 0, is this also true approximation? Unfortunately, that's not always the case. But if f spans exactly k vertices, and if V is the smallest subset in the calligraphic L that contains the optimal solution, then we can prove that f is indeed a true approximation. The first question one might ask is whether there is always a lambda that results in a tree spanning exactly k vertices. Unfortunately, this is not the case. What we can show, though, is that there is always a lambda that, depending on the order of concurrent events that are processed, we can end up with either a tree spanning at least k vertices or with a tree with less than k vertices. The execution path of the algorithm diverges on the rare occasion of concurrent events. Hence, we employ a lookup tie-breaking list tau to guide the execution path, where each entry of the list is either an edge or a subset, and the if entry in the list gets the highest priority among concurrent events in the if iteration. Adding to the previous flowchart, we now have that the penalties are increased by a lambda, and that the algorithm checks the list tau to decide which event it should process in the case of concurrent events. Denote by tau tilde the list tau without its last entry. Then our objective now is to find a tuple lambda tau such that running the algorithm with lambda tau returns a tree spanning less than k vertices, and running the algorithm with lambda and tau tilde returns a tree with at least k vertices. We call such tuple a threshold tuple. Okay, but how can we find such threshold tuple? We present the search with an example. We start with an empty list tau, and we know that for lambda equals to 0, we find a tree with less than k vertices, and that there is a large enough value for lambda where we find a tree with at least k vertices. We then analyze the time it takes for each edge and subset event to be processed at the first iteration of the growth phase. Since the increase in the y variables is uniform, the time for the events behave as straight lines. In this example, we observe that in the open interval between 0 and 615, the first event is the event of subset L2, and that for lambda greater than 615, the first event is the event for edge E1. We note that at the value of 615, the two events are concurrent, and in this example, giving priority to L2 in the first iteration, uses a tree with at least k vertices. Hence, we include L2 in our tie-breaking list. Note that now, any execution of algorithm with lambda in the interval between 0 and 615 processes the subset event of L2 first. Thus, we reduce the search to this interval and repeat the process for the second event. Now, we observe that the open interval between 0 and 142, the second event is the event of subset L4, and that for lambda in the open interval between 142 and 615, the second event is the event of edge E4. Note that the value of 142, the two events are concurrent, and the algorithm finds a tree spanning less than k vertices by giving priority to edge E4 at the second iteration. Hence, we include E4 into the list and again reduce the search interval. Observe that now the second event is guaranteed to be the event of edge E4. We now look at the events for the third iteration of growth phase, and in this example we find that in the open interval between 232 and 286, the event L6 is processed, and that at the extremes of this interval, the algorithm returns two distinct trees when L6 is given highest priority in the third iteration, one with less than k vertices and the other with at least k vertices. Hence again, we include the subset L6 in the tie-breaking list tau, and we are ensured to have it processed in the third iteration of the growth phase. Now, because the number of events processed in the growth phase is finite, we are ensured to find a threshold tuple at some iteration. The argument for the events to behave as line segment follows from the linearity of the summation of the variables of the vector y, and for the fact that up to the if iteration of the growth phase, the same sequence of events are processed for any value of lambda in the search interval. Therefore, if we do not find a feasible true approximation at first, that is, if we do not find a tree spanning at least k vertices with lambda equals to 0 and an empty tie-breaking list, then we can find a threshold tuple. We now state the main property of a threshold tuple. Let sigma be the last element in the list tau. Consider running the growth phase for lambda tau and lambda tau tilde, and let y and y prime, f and f prime, b and b prime be the computed vectors, trees, and tight subsets from these executions. What we observe is that the execution path of the two growth phase diverge just slightly and then they converge again. And we can prove that both y vectors are the same. That if the last element of the list is an edge, then the collection of typed subsets B are equal, and the trees are different in exactly one pair of edges. And if the last element is a subset, then the two trees are equal and collections B differ in exactly one subset. Somehow, this small difference in the two executions leads to a final tree spanning different amount of vertices after the pruning phase. We now show how to obtain a tree spanning exactly k vertices from the case where the last element in the tie-breaking list is an edge. We omit the subset case in this presentation. Suppose we have a threshold tuple, then, by the previous lemma, we obtain two trees that differ in exactly one pair of edges. We highlight them with the color of blue and orange. After pruning each of them, we obtain one tree spanning less than k vertices and the other with at least k vertices. Let's call the top tree, the one spanning less than k vertices, the blue tree, and let's call the bottom tree, spanning at least k vertices, the orange tree. By merging the two trees obtained after the growth phase, we obtain a new graph that contains exactly one cycle, and it can be shown that no subset containing a vertex from the cycle in the collection of tight subsets B has degree 1 on this new graph. Hence, after pruning this graph, it must also contain the cycle. It must also span at least k vertices, because it is a supergraph of both blue and orange trees. Now, if we remove the orange edge, we end up with a tree that is a supergraph only of the blue tree. Hence, if we prune it again, we obtain the blue tree spanning less than k vertices. We then select from the ones deleted from the second pruning phase to obtain a tree spanning exactly k vertices. By carefully picking the vertices, we show that the new tree satisfies certain conditions which agree partially with the hypothesis from lemma 2, which is the lemma that bounds its cost. We now have a tree F spanning exactly k vertices. To finally use lemma 2, we also need V to be the smallest subset in the calligraphic L that contains the vertices of an optimal solution. Since calligraphic L is binary laminar, we can throw away the greatest subset in it without the root and run the whole process again. For example, if at first we run the algorithm but fail to satisfy the smallest subset criteria, we can delete a subset that spans no vertices of the optimal solution and reduce the instance. Trying a second time, if we fail to satisfy the criteria again, we can delete a subset without the root and reduce the instance once more. Because we delete at least one vertex per reduction, at some iteration we must satisfy the criteria. This is a flowchart that summarizes the whole procedure. While G contains at least k vertices, we first try to obtain a tree with lambda equals to 0 and empty type breaking list. If this fails, then we can find the threshold tuple and compute the tree spanning exactly k vertices and reduce the instance by throwing away a subset that does not contain the root in the calligraphic L. At some point, the graph becomes too small and the execution ends. And by lemmas 1 and 2, the cheapest among all the computed trees must be a true approximation. Thus we obtain the main result from this paper. There is a true approximation for the k prize collecting Steiner tree. Thank you.
Thank you, Hugo. Now we have some time for questions. Marcelo?
Hello.
We can hear you. You can say.
Hey Hugo, what is the strategy of the other algorithms for this problem, and do they also focus on the solution giving exactly k vertices?
Not really. I don't quite recall there is a 5 approximation and a 3 point something approximation. The 5 approximation is based on a Lagrangian relaxation. I don't quite recall if it finds a tree with exactly k vertices. But the other one, it basically obtains two trees. It first runs your favorite price collecting Steiner tree algorithm without that is the same problem without the restriction for the solution to have at least k vertices. And if it does not contain k vertices, it simply looks for another tree that spans at least k vertices. So it runs you run the best algorithm for the price collecting Steiner tree and the best algorithm for the k minimum spanning tree, and then then the solution is obtained by merging both.
Mm-hmm. Okay. Because it seems a little, I don't know, kind of loose, looking for a solution with exactly k, and I just wanted to know if the other algorithms look for this kind of structure too.
Well, one interesting question about we might say that's an open problem, is that in this problem we ask for a tree that spans at least k vertices. We don't know we don't know if there is an algorithm to find we don't know if there is an approximation algorithm to find a tree that spans exactly k vertices every single time, because in our algorithm, if we find a tree spanning at least k vertices on the first try, we already stopped the execution, and that's enough for us. But and the rest of the algorithm depends on relies on the fact that we did not find a tree that spans at least k vertices on the first try. So we don't know if we can find a tree. We can always find a tree that spans exactly k vertices.
Okay, thank you.
Are there any more questions? Any other question? If not, then let me thank you again